Dear students, welcome to my channel. In today's lecture, we will learn about fluorometry. Let's start. Here, we can easily understand the phosphorescence and luminescence and fluorescence by watching this video. In this video, we learn that uh, these are phosphorescent. When light is provided upon them, then usually this glitters light. Okay, this fluoresces. And we'll also see that whenever light is stopped, then this also provides light for some time. Let's see the video. So they are glittering, so that's why these are called fluorescence. Okay, but when the light is stopped, it also appears. This is called phosphorescence. So this is uh, fluorescence and this is phosphorescence. So let's see some definition. Luminescence is the emission of light by a substance. It occurs when an electron returns to electronic ground state from an excited state and loses its energy as a photon. It can be of three types: fluorescence, phosphorescence, and chemiluminescence. So in this case, we can see here, uh, this is an instant method, fluorescence. Okay, but in case of phosphorescence, we have seen that this also appears whenever light is cut off. Okay, phosphorescence appear for longer period of time. For example, for 640 seconds it appears still. Okay, so these are phosphorescent and these are fluorescent. So when a beam of light is incident on certain substances, they emit visible light or radiation. This is known as fluorescence. Fluorescence start immediately after the absorption of light and stop as soon as incident light is cut off. First observation of fluorescence from a quinine solution is in sunlight was reported by William Herschel. Quinine in tonic water is excited by UV light from the sun. Upon return to the ground state, the quinine emits blue light with a wavelength near 450 nanometer. Emission rate of fluorescence are typically 108 per second. So a typical fluorescence lifetime is near 10 nanosecond. Fluorescence is much more widely used for chemical analysis than phosphorescence. When a light radiation is incident on a substance, it emits light continuously even after the incident light is cut off. So this is called phosphorescence. The substances showing phosphorescence are known as phosphorescent. Emission rate of phosphorescence are slow and lifetime is typically millisecond to second. Chemiluminescence, as the name suggests, luminescence due to chemical reaction. So emission of light as a result of chemical reaction at environmental temperature. Chemiluminescence is the generation of electromagnetic radiation as light by the release of energy from a chemical reaction. A standard example of chemiluminescence in the laboratory setting is the luminol test. Here blood is indicated by luminescence upon contact with iron in hemoglobin. It's called as cold light. So let's discuss bioluminescence. It is the production and emission of light by living organism. When chemiluminescence takes place in living organism, the phenomenon is called bioluminescence. It occurs widely in marine vertebrates, invertebrates, as well as in some fungi, microorganisms, including some bioluminescent material, bacteria, and terrestrial invertebrates such as fireflies. So let's discuss the differences between UV visible spectroscopy and fluorescent spectroscopy. As we have learned that UV visible spectroscopy is the most commonly used um, analytical technique used in our pharmaceutical area. We use this for assay, analysis, quantification, qualification. For every other aspect we use this. But then why fluorescent? We'll see in this difference that fluorescence spectroscopy is more specific, more robust, and more uh, sensitive than UV visible spectroscopy. That's why fluorescent spectroscopy is sometimes used. So let's say different basic differences. So measure absorption of UV visible radiation by molecule. It measures emission of light from excited molecule. So here electronic transition occurs. Here electronic transition due to emission after excitation occurs. So it's analytical technique based on absorption of electromagnetic radiation. It's analytical technique based on fluorescence emission. It measures the absorbance or transmittance, but it measures the fluorescence. Sensitivity is low. Detection level is high, but its sensitivity is very high. Detection level is low because it can measure in nanogram or picogram level. So you can easily understand how sensitive is fluorescent spectroscopy. Reference beam requires a reference beam, but it doesn't require a reference beam. Selectivity low and its selectivity is high. Then it's less specific, highly specific. So more interference from impurities, but it has less interference. That is, impurities can impact this spectroscopy. Okay, less interference. So this is better. So requires higher concentration, but it requires very dilute concentration, as we have already seen that nanogram or picogram level. So effect of temperature is minimal, but in this case it's very sensitive. That's why it has very much effect on temperature. So solvent effect is minimal, but in this case, as it is very sensitive, it has larger effect. So its cost would be overall low, but its cost is expensive because it is highly specific and sensitive. So instrument complexity, it's simple, but it's more complex. That's why it's very expensive. So in application, we use this for assay dissolution, but you use this in trace drug estimation. Okay. Example is the common drug are analyzed in this, but in case we see the riboflavin, quinine, fluorescein, these are some uncommon drugs which are analyzed by this. However, there are a number of similarities between these two spectroscopies. So we'll learn this. Both of them uh, use UV visible region radiation. Both of them electron are excited in both of the cases. Both of them are non-destructive. Both of them are analyzed the product in solution form. Both of them can undergo both qualitative and quantitative research used in pharmaceutical analysis. Both of them depend on molecular structure. That's why in UV visible spectroscopy we have seen chromophores, but in case of fluorescent we have seen fluorophores. Effect of solvent and pH, both of them has impact. Both of them follow Beer-Lambert law. Both provide faster analysis with minimal sample preparation. In both of the cases, the instrumentation is similar, like light source, monochromator, sample cell, detector, signal processor. These are common in both of the instrumentation. So both of them are used in QC and R&D. So let's see the fluorometry. It's an analytical technique for identifying and characterizing minute amounts of substance by excitation of the substance with a beam of UV visible light. It is also called spectrofluorometry or fluorescence spectroscopy. So UV visible spectroscopy is called spectrophotometry. It is called spectrofluorometry. Is a technique in which UV visible light is absorbed by electrons in singlet ground state to move to singlet excited state and returns back to the singlet ground state by emitting radiation with lower energy or same energy to give rise to fluorescence spectroscopy. It can be of two types, excitation and emission spectroscopy. Molecules are able to absorb electromagnetic radiation as UV visible region and raise to the excited state. The reverse process, that is loss of energy and concomitant transition of molecules from excited to the ground state, can occur with emission of radiation. Such emission is known as fluorescence or phosphorescence depending on the condition of emission. The intensity and composition of the emitted radiation can be measured, and such measurement form the basis of sensitive method of analysis called fluorescence. So here we can easily understand the mechanism if we follow this. This is a molecule. Whenever we are applying some radiation Okay, UV visible spectroscopy, then what would ultimately happen? The electron will go from the ground state to the excited state. So this is a higher energy state and very unstable state. So electron will not be here for more time because this is an unstable condition. So they come into the lower level, and from there it comes again into the ground state. Okay, whenever it is coming to the ground state, this is emitting radiation. So this is the upcoming radiation, and this is the fluorescence that we are analyzing. Okay, so this is the overall method for UV visible spectroscopy, for fluorescent spectroscopy. If we see, uh, if you see in this diagram, we can easily understand that this is the ground state, these are the excited state. So it can be of two types, like singlet excited state and the triplet excited state. So there are a number of levels we can see here. So here, whenever electron is absorbing radiation, it is coming into the singlet excited state from the ground state. So there internal conversion happens and vibrational relaxation happen. So whatever their level is, they come into the lower level. So why coming into the lower level? Because the lower level is much more stable. Okay, in some cases some of the electron comes in triplet excited state. Okay, so whenever electron are coming from the this state to the ground state, then we see the fluorescence. But whenever they are coming into the triplet excited state, then this is called intersystem crossing, and we are getting phosphorescence by this. Okay, so that's how we see fluorescence or phosphorescence. In that case, again another phenomenon is that the phosphorescence takes some time, because for intersystem crossing, electrons are coming from here to there, and this delays some time. Okay, that's why phosphorescence appear in a delayed manner. So let's see the principle. Molecule absorb UV visible light, irradiated and raised to the excited state. Such excited state has different vibrational energy level, and excited molecules are distributed in various vibrational levels. One of such excited state is called singlet state. Singlet state is defined as the excited state in which the electrons are paired, and in each pair two electrons spin about their opposite direction. Molecule cannot stay at the excited state for a long time. Average lifetime of a molecule in the singlet state is 10 to the power minus 8. So what will ultimately happen? They will come down to the ground state. So molecule at each vibrational level of excited state lost energy and return to the ground state. In this case, the energy and hence the wavelength of emitted light is not exactly same as absorbed. The molecules undergo a repeat process, a radiationless loss of energy, and quickly fall to the lowest vibrational radiation level. This process is called vibrational relaxation. From the lowest vibrational energy level of the excited state, a molecule can return to the ground state by photoemission or by radiationless process. Okay, so they come into the vibrational the lowest vibrational level, and after the lowest vibrational level they come into the ground state. If the molecule return to the ground state by emission of radiation, then the process is called fluorescence. Other processes involving the excited state can occur to compete with the fluorescence emission, and not all of the absorbed energy will be emitted as fluorescence. So another term is intersystem crossing. A molecule in the lowest vibrational energy level of the excited state converts to triplet state lying at an energy level intermediate between the ground and excited states. It is characterized by unpairing of two electrons. From the triplet state, a molecule can drop to the ground state by emission of radiation. This type of luminescence is called phosphorescence. So this is the ground state, most stable state. This is excited singlet state, and this is excited triplet state. We can see here ground state, this is the excited singlet state, no magnetic field appears, spin paired but in different level in excited state. But in triplet state they are much you can see their magnetic field exist. Why? Because they are both in unidirectional. So these are the explanation of ground state, singlet excited state, triplet excited state. So this is the theory of fluorescence. First of all, excitation, then internal conversion and vibrational relaxation, and lastly, fluorescence. So here the overall figure has been shown. And the theory of phosphorescence include one extra step, that is the intersystem crossing. This is the additional step in regard to fluorescence spectroscopy. Transition occurred from the excited triplet state to ground singlet state. It's characterized by an afterglow due to the long life of triplet state. It has happened as a favorable condition such as low temperature and absence of oxygen. So let's see the luminescence. Luminescence is the emission of photons from electronically excited state. Luminescence is divided into two types. In a singlet excited state, the electron in the higher energy level has the opposite spin orientation as the second electron in the lower orbital. These two electrons are said to be paired. Return to the ground state from the excited state doesn't trigger an electron to change its spin orientation. Okay, because in singlet state we have already seen their direction is still opposite, but in triplet state their spin is unidirectional. These electrons are unpaired, that is, these spins have the same orientation. A change in the spin orientation is needed for a triplet state to return to the singlet ground state. So this is photoluminescence. One is prompt fluorescence and another is delayed fluorescence and another is phospholuminescence, as we have already discussed. So let's see the relationship between the fluorescence and structure. So there are a positive or negative relationship between this fluorescence and structure. We'll discuss this. Definite correlation between fluorescence and chemical structure can't be made. Generally, fluorescence is associated with extended chromophore or oxochrome and a rigid structure. Structural features that influence the degree of conjugation of a molecule and the delocalization of pi electron also influence the fluorescence characteristics. We have seen in our previous lecture that degree of conjugation and degree of delocalization of pi electron is much more influencing in UV visible spectroscopy. As we have already discussed, this fluorescence and UV visible spectroscopy are somehow similar in case of their principle. So this happen in case of fluorescence spectrometry also. Saturated compounds such as cyclohexanes are non-fluorescent because no double bond appears. While benzene is weakly fluorescent or nearly non-fluorescent, and highly unsaturated polycyclic aromatic compounds such as anthracene are strongly fluorescent because of conjugation. So we can see here that overall the unsaturation will lead to the fluorescence and UV absorption. Substitution on benzene ring can influence fluorescence property of a compound in a number of ways, such as monosubstitution of benzene with alkyl group was found to have little influence on the intensity of fluorescence. So substitution with some groups known to increase the electron localization, such as chloride, bromide, iodide, yielded to compounds that are found to be non-fluorescent. So let's see what is happening. For example, this is a benzene ring. Okay, this is the delocalized electron. So for example, we are adding here some electron donating group. We know the electron donating group are amino group or hydroxyl group, okay, or methoxy group. These are the electron donating group. So what will they do? They will ultimately donate electron to the benzene ring. Okay, they are also called benzene ring activating substituent. They are activating the benzene ring. They are also called orthopara determiner. Okay, so whenever any substituent is activating the benzene ring or any substituent is donating electron to the benzene ring, this will ultimately stabilize the benzene's unsaturation, that is delocalization. Okay, that is why this is helping the benzene ring and this is creating fluorescence. Okay, so we can see here that NH2, OH, OCH3, they are fluorescence. Why? Because they are providing electron, donating electron to the benzene ring. Then benzene ring is stabilized, and as something is stabilized, that would be fluorescent. They are also orthopara determinant. But if we see a different scenario when For example, it is a benzene ring and the substituent are not electron donating, rather they are electron withdrawing group. For example, COOH. These are electron withdrawing group because of the oxygen. Then NO2, nitro group, or we can see some sulfonic acid derivative like SO3H. So you can see here there are a number of electronegative groups. What will they actually do? They will ultimately take the electron from the benzene ring. So they are deactivating the benzene ring. So they are also the meta determiner. Okay. So whenever COOH, NO2 or SO3H, this group appears in the benzene ring, then they will deactivate the benzene ring. They will deactivate the delocalization of the benzene ring, and they will make the structure non-fluorescent. Okay, they will inhibit the fluorescence. So this is the overall uh, basics of relationship between the fluorescent and structure. So compound with fused ring are found to be specially fluorescent, and the extent of fluorescence is found to be directly proportional to the number of rings of the molecule. So you can see here, if the more heterocyclic numbers, the more would be the fluorescent. It was found that doubly bonded nitrogen in a ring tend to decrease the likelihood of fluorescence, while the presence of NH, O or S appeared to contribute to the likelihood of fluorescence. Structural rigidity in a molecule favor fluorescence. That's why fluorine is fluorescent, but biphenyl is not. Fluorescein is fluorescent, but phenolphthalein is. So let's see. This is a rigid structure, but in this case, we can see this linkage has gone off. Okay. So what will ultimately happen? This is not a rigid structure, but this is a rigid structure. So what will ultimately fluoresce? This fluorine will ultimately fluoresce. Another example is fluorescein and phenolphthalein. Okay, we can see the linkage. Due to the linkage, there is a connectivity between the conjugation, but the linkage is dissipated in that case. So this is not a rigid structure, but this is a rigid structure. So this will fluoresce. There are more other examples of fluorescent or photoluminescent materials. However, there are a number of factors affecting fluorescence, as we have already discussed some of the factors regarding the structure. So first of all, nature of the molecule. All the molecules cannot show the phenomenon of fluorescence. Only the molecules which absorb UV visible radiation can show this phenomenon. We have discussed this in the similarities between UV visible spectroscopy and fluorescence. Greater the absorbance of the molecule, the more intense its fluorescence. Nature of the substituent, we have already discussed that electron donating group enhance fluorescence, but electron withdrawing group decrease the fluorescence. Moreover, high atomic number containing atom introduced into the pi electron system decrease fluorescence. Okay. Concentration of the fluorescent species. The intensity of the fluorescence increases as the concentration of the fluorescent species increases. We know it follows or it obeys the Beer-Lambert law. So A is equal to ABC. Okay. Then adsorption. Just think, we are keeping the product in a solution, the substance in a solution. Just think that we are providing radiation and we are getting transmittance or fluorescence. But think a scenario when the fluorescence light or the upcoming light would be absorbed by the glass or by the cuvette. Then what will happen? This material will not get the incoming radiation. So this is actually happening. Absorption of the fluorescent substance on the container wall creates serious problem. Okay. Then oxygen. So oxygen, the presence of oxygen will obviously interfere. For example, think that we are analyzing in a cuvette. Okay, so your substance are having some dissolved oxygen. So obviously, this oxygen will interfere the fluorescence by direct oxidation of the fluorescent substance to non-fluorescent, and by quenching of the fluorescence due to the paramagnetism of oxygen. So we'll discuss this later, the quenching. Then pH. pH alteration of the solution has significant effect on fluorescence. Fluorescent spectrum is different for its ionized and unionized species. Most phenol are fluorescent in neutral or acidic media, but the presence of a base lead to the formation of non-fluorescent. Then temperature. Okay, let's think another scenario. For example, this is a cuvette. In this cuvette we are analyzing a sample. So whenever the temperature is increased, for example, due to some reason its temperature has increased. So when its temperature is increasing, what will ultimately happen to the system? The movement of the particle will increase. Okay, as the movement will increase, then it will create some collision, and due to the collision, the upcoming radiation and the outgoing radiation would not be optimized. So increasing the temperature increase the thermal motion, then increase the collision, then this helps in dissipation of excited energy. So increase in temperature will ultimately decrease the fluorescence. Then inner filter effect. If non-fluorescent solutes absorb either excitation or emission radiation, there is a reduction in measured intensity of the fluorescence. So let's discuss the quenching, one of the important factors affecting the fluorescence. Quenching. So what do we mean by quenching? First of all, we need to learn what is the actual meaning of quenching. So quench means decreasing or fulfilling something. Okay, decreasing something. We sometimes use the word that uh, this quench my thirst for knowledge. Okay, quench my thirst. Okay, quench means to removing something or decreasing something. So decrease of fluorescence intensity by interaction of excited state of the fluorophore with the surroundings is known as quenching. It can be of different types like self quenching, chemical quenching, static quenching, and collision quenching. So let's discuss one by one. First of all, self-quenching. As the name suggests, self means itself. Okay, if the material or the substance itself responsible for the quenching or decreasing the intensity of the fluorescence, it's called self-quenching. So deviation at higher concentration can be attributed to self-quenching or self-absorption. For example, we are using a compound at lower concentration. Okay, very good. It is showing some linear response. But think another response that we are uh, we have increased the concentration of the sample, then what will ultimately happen? At a lower concentration it will show linearity, but at higher concentration it will not ultimately show any fluorescence. Okay, so at higher concentration it will not show any absorbance or fluorescence. This is called self quenching. Itself it is responsible for its high concentration and decreasing intensity. Then chemical quenching, we have already discussed this. Due to the oxygen, we have seen the decreasing of intensity. Due to the heavy metals, it can lead to quenching. Okay, some halides, okay, nitro group or carboxyl group, these are electron withdrawing group, and these will ultimately decrease the intensity of the fluorophore. Then the pH. pH should not be too acidic or too basic. It should be within a buffer range. The next one is static and collision quenching. So let's think a scenario. These are the ground state and these are the excited state. So electrons are coming into the excited state from the ground state, and when they are coming into the ground state, they are releasing fluorescence. So this is an overall scenario. So when some quencher attack the electron in the ground state, it's called static state by static quenching, because these are the static level. Okay, and in case of higher energy, the electrons are moving, they are in excited condition. If some quencher attacks the electron in that region, this is called collisional quenching. Why collisional? Because they are still in high energy state, and in that case any quencher came to here and this will ultimately decrease the radiation, because whenever quencher is come, then this electron will not come back to the ground state and they will not fluoresce. Okay, so it is the process where quencher binds with the fluorescent molecule in ground state and inhibits the molecule to go to the excited state. For example, caffeine reduces the fluorescence of riboflavin by complex formation. So this is a quencher. Caffeine is a quencher in this case. And in case of collisional quenching, it's the process in which quencher binds with the fluorescent molecule in excited state and transfer of energy to quenching molecule occurs. So let's discuss the fluorescent spectroscopy. So fluorometry or spectrofluorometry is a type of electromagnetic spectroscopy which analyzes fluorescence of a sample. It involves the use of beam of light, usually ultraviolet light, that excites the electron of the fluorescent molecule and causes them to emit light of a lower energy visible light. So device is called fluorometer or fluorometer. So this is the basic instrumentation of fluorometer. In that case, a notable thing is that the detector is angled at 90 degree. So why 90 degree? Because whenever uh, if think a scenario, if we set the detector here, what would ultimately happen? This will ultimately interact with the light source. Okay, this transmitted radiation would interact with the light source because this is a case of fluorescence. This is not absorption. If it would be absorption like UV visible spectroscopy, we can keep the detector here, no problem, because we are analyzing the absorbance. But in the case of fluorimeter or fluorescence spectroscopy, we are analyzing the fluorescence. Fluorescence means some light radiation. Okay, so we are analyzing the light itself coming from the sample. Just think, if we keep this in 180-degree angle as like this in this path, then what would ultimately happen? We would ultimately get the incoming radiation, very good, but in the meantime we would ultimately get the radiation coming from the light source. So these would ultimately interact with each other. So that's why we are keeping this detector at 90-degree angle. Okay, so whenever something is in 90-degree angle, so we can easily observe this. For example, uh, during cricket match, we see the second umpire appear in this direction. Okay, for greatly overviewing the run out. Okay, but the first umpire cannot easily check the run out because the bowling and batting is very much visible whenever umpire is in 90-degree angle. Okay, he can easily understand that what is going on. So this is the same case for our detector in fluorometer also. So this looks like an ampere. He is just observing what is happening here. So the instrumentation are as same as UV visible spectrometer, the light source, monochromator, sample holder, detector, readout device. So instrumentation also shown here. So source of light, xenon arc lamp, tungsten lamp, filter and monochromator. Most common type of monochromator utilizes a diffraction grating. A spectrofluorometer usually has adjustable excitation and emission wavelength via monochromator. So it can be of excitation monochromator or emission monochromator. So sample cell, it contains the sample. Then the detector, it detects the upcoming fluorescence. It can be of different types like photovoltaic cell, phototube cell, photomultiplier tubes, etc. So let's see some applications of fluorometry in as fluorescent indicator in pharmaceutical analysis, determination of vitamin B1 or B2. Then in liquid chromatography like SPLC, it can be used as detector in organic analysis, both in qualitative and quantitative analysis, in determination of inorganic substance also, in tracer technique, in SFS, that is spectral fluorescent signature. So these are the some advantages of fluorescent spectroscopy. As we have already discussed, it is very sensitive, very specific, and wide range of application it has. So there are some disadvantages also. Not only its high cost, but also it is not suitable for identification. Not all compounds fluoresce. Contamination can quench the fluorescence and hence give false or no result. We have discussed in separately the quenching. So these are all from our fluorescence spectroscopy. If you have any confusion, please inform me in the comment section. Thank you.